Good morning, gentlemen. It's a pleasure to be working with you. We're here to record a session for the Greenroofs.com virtual conference on water, wind, heat, and grow. We have a distinguished panel of speakers today, including David Aponte, Kevin Songer, and Joe Webb, and myself. And we're each going to make brief presentations and then follow that up with some questions and dialogue amongst our group to help you understand a little bit about the living systems on rooftops and some issues with weather that we might have that are related to the growth media and the planting systems that we're using. It should be a very interesting discussion because I'm in the Midwest, David is in Puerto Rico, Kevin is in Florida, and Joe is in Houston, all with different climates and microclimates and different concerns about wind uplift and some of the growing conditions. You'll see on my first slide here, one of the issues that we do have with rooftops can be wind uplift. This is following a hurricane, on the periphery of a hurricane. Some years ago, I got this slide from the National Roofing Contractors Association, here showing wind uplift of shingles. And you can imagine if you put a green roof on top of a facility like this, there could be some issues with that. In a green roof system, you know, here I'm showing our Student Success Center on campus. This is a 16,000 square foot modular green roof system. It's green roof blocks. These are sedums. This is just after installation in August of 2009. You notice there are parapet walls. I'm going to call your attention to this air conditioning vent or louver over the top of some of the air exchangers in the building, because this will become relevant to a wind uplift event that we had on campus here a little later in my presentation. But you can imagine we're putting things on the rooftop. They're not secured. They're just sitting there. What are the concerns with the growing conditions, the media, and the plants, and what about wind uplift off the roof? So it happens that on our campus we have a subsonic recirculating wind tunnel. The facility here is in our engineering building. It's what was purchased from Engineering Laboratory Design, and we're able to, inside the wind tunnel, achieve wind speeds, direct line wind speeds of 200 miles per hour. We can increment those starting at 0 all the way up to 200 by controlling the electric current supplied to the large fan. Here you can see the wind tunnel test being set up. We've got an EPDM membrane inside the facility here. We've placed a green roof block. This one is fully vegetated. Inside the tunnel, the wind comes from this direction and flows this way over the top of the block. For the purposes of our test, the blocks are secure on the roof. What we're evaluating for what we did was wind uplift of the plants and the growth media. Here you can see we've posted a sign. This module that is tethered by a rope and also tape on the EPDM membrane is experiencing straight line winds of 140 miles an hour. You'll notice that we have angled this at a 45-degree angle into the wind because, according to the National Roofing Contractors, this is where the most turbulence is on the roof, and we're interested in what sort of wind uplift. We've achieved 140 mile an hour wind speeds with no blowback or blow off of the media or the plants in this system. However, in a green roof media that's aggregate based, this is Arcolite with 80% Arcolite, 20% composted pine bark. This is a wind tunnel test after a 30 mile an hour wind on the corner down here. And you'll notice here there are two vortexes where the wind uplift has scoured the media off and blown it into the end of our wind tunnel. And we collected that on the screen, and it's a significant amount of growth media. So unsecure growth media is an issue. We looked at some methods to control wind scour, including several liquid binding agents, some commercial burlap, and some commercial netting. And in fact, one of the binding agents we've used We just saturated it, allowed it to stand for 24 hours, and it actually bound the media down and put it in the wind tunnel. Same 140-mile-an-hour wind gust. No media blew out of this particular module, and we've since tested this on our roof, and we've applied it over the top of the plants with no phytotoxic effect, and we get 100% coverage after about 9 months on the roof of the plants. They just grow right through it or around it, and we still have secure media. So we feel like this is a really effective way to hold the media on the roof. In terms of a partially vegetated module, same thing with the liquid binding agent. Again, this tests at 140 miles an hour. You can see the plants are bent over. We're looking down on top of it, whipping along, but no wind scour. So we're able to actually use this agent to hold the media and the plants in place. So our conclusions from our tests is that fully vegetated modules reach wind speeds of 120 miles an hour for 5 minutes with no displacement of growth media. Wind scour occurred at wind speeds of 30 miles an hour test with modules containing growth media only. And wind scour occurred after reaching wind speeds of 75 miles an hour when we tested partially vegetated modules with less than 100% coverage. So using those first findings, we went back and looked at some liquid binding agents, and either binding agent, which allowed the plants to go through, or burlap to hold the media down and planting through it, we were able to secure the media on the roof with no wind scour. Now, since our testing, there's been in North America the passage of ANSI SPRI RP14 in 2010. I believe it goes into effect in 2013. There needs to be further testing of individual components and total systems. I know David was asking me if we had done these at different saturation levels, and I'm hoping he's going to talk a little bit about that. Joe, you're in a building at 9 stories. On my campus, the tallest building is 4 stories. We're constrained by our architects. So different building heights, roof slopes, and exposure categories, roofing systems, corner area, roof field can all affect how green roofs survive in terms of the planted systems and also how they respond to water, wind, and heat. So we did have a wind event here. That same module that I showed you on our roof that's covering the air conditioning event, we had an F1 tornado go by here with a wind speed estimated in our area of over 80 miles an hour, and it blew this particular piece that I'm pointing at completely off the building of the roof. It was secured, it unsecured it and went over the edge. The edge here, there are 4 blocks between this module and the edge. Over here, this is the damage where it bounced over the roof and then went over the side, but none of the modules on the roof and none of the media left the facility. Only this particular piece that blew off. So we've had a wind event here. Fortunately, no injuries, no damage to the building, and they've since replaced it. So I'm going to moderate our session. I just wanted to give a start about what we were doing. I am the research coordinator for the Green Roof Environmental Evaluation Network at SIUE. We have a number of students working on about 15 green roof projects, looking at stormwater, plant growth, and that. I'll be asking questions of our speakers as we go through. And our next speaker will be Kevin Songer from Florida. So Kevin, the floor is yours now, please.
Thank you, Bill. And thank you, David and Joe, for serving on the panel. I grew up in South Florida and witnessed many hurricanes coming ashore in the Miami area. I can remember trees being toppled over, and down in Florida, the houses typically had built-up asphalt roofs with gravel ballast on top, and when a strong hurricane would come across, it would pick up and throw the ballast off the roof. So I have a very deep interest in Cyclone Alley, as I call it, here in Florida. By education, I'm a lawyer and a botanist, and I love green roofs and choose to approach green roofs from the perspective of what plants work best for green roofs in hot and dry and windy climates. Worked very closely with the University of Florida, Dr. David Previtt, in hurricane testing green roof panels at the university using outdoor positive pressure system. This system has 8 turbines with several large, very big diesel generators that blow the rooftop, simulating hurricane winds. Another factor that we look at here in Florida is rooftop systems that have very good drainage. That's important. We in Florida typically receive between 45 and 60 inches of rain every year, which is almost double what Chicago or some of the areas in the Midwest might get. But most of that rain comes in just a few number of large rainfall events. And so we may go through very long periods of drought, up to 9 to 12 weeks. It's not uncommon to have 12 weeks of little or no rain, and then all of a sudden we'll get a huge event. So when your rooftop garden receives 8 to 12 inches of rain, it needs to be designed to handle that kind of volume. I like to say here in Florida, there's nothing like a Florida roof with respect to growing plants. We have what I call the 7 H's. We have hurricanes, extremely high humidity levels. We have unbearable heat, just like the rest of the nation. Very hard freezes. We have hot, desiccating, drying winds that can really impact green roof plants. We have extremely high temperature swings. Sometimes in the spring it can go from below freezing up to well over 100 degrees Fahrenheit on a roof during the afternoon. And we have high available daylight, all of which impact our green roof design and selection of the green roof plants. Many people have tried sedum here in Florida, and sedum typically has not been a successful plant choice here in Florida. This is a picture of a 10,000 square foot roof in Jacksonville where sedum was brought in from up north, and it was planted in October of 2010 and dead within a month, and did not come back the following spring. Did not die of frost. We have here an issue that sedum falls susceptible to southern blight fungus, and with the high humidity levels and the high afternoon temperatures, most succulents, especially soft fleshy succulents, fall victim to southern blight fungus. So our focus, especially mine as a plant person, botanist, has been what kind of plants can I use on a Florida green roof that will survive the 9 weeks of drought, will survive the hurricanes, the cyclone winds, that will come back year after year, afford greenery in the wintertime, survive the humidity, and especially adapt to the strong desiccating winds that we have here. And what we found that's really helped us with our success is we focus now on trying to provide biodiversity at higher taxa. In other words, when we first started off with green roofs, we might use most of the plants out of the Asteraceae family. And although there are many species in the aster family, it's just one family. And what we've come to realize is that there's a basic rule we can follow. We call it the 10-20-30 rule that mimics very complex ecosystems. And the 10-20-30 rule is on our roofs we provide no more than 10% of any one species, 20% of any one genus and 30% of any one plant family. So we get a good broad-based mixture of plants. That seems to really help with our success. And we actually picked that up from studying Mother Nature. This is a picture of the limestone wall at Castillo de San Marcos in St. Augustine. And we took a 3 meter by 3 meter square and identified over 50 species of plants, 30 different plant genus, and 20 different plant families. And that was really the beginning of our 10-20-30 program, or search for biodiversity at higher taxa. And by implementing biodiversity at higher taxa, we've been very successful in having long-term plant growth on green roofs. This is our most recent project, and there's a wonderful project website at greenroof.com. It's an educational roof. Students use it all the time. But we have 37 plant families, 84 plant genus, and over 100 different species. Right plant, right place is the approach we take, because we do not add supplemental irrigation or fertilization. Our roofs stand on their own with just what I call nature irrigation. That's water, vapor, fog, and dew, and rainfall. But we typically, first of all, look at what we feel are the two most important design variables for green roofs, and that's light and wind. And we'll break down a roof into a grid system that shows levels of light and levels of wind. And from there, we'll take and identify which areas are the windiest with the strongest light. We call that the dead zone, and put the plants that are most capable of surviving there. There's a host of many secondary variables that we look at: allelopathic, leaf droppings, and shade, and other factors, but light and wind are the primary ones that we study. Once we've tracked those grids on the roof and determined which are the brightest and the windiest spots, then we look at our three types of plants we're working with: C3, C4, and CAM photosynthesis type plants. C3 plants are the fastest growing. They'll fill in, but they're also the most susceptible to desiccation, because most of the photosynthesis occurs directly on the leaf surface. So we put those interior in our plantings. The C4 plants, they typically break down photosynthesis into subcomponents that the processes occur within vacuoles embedded in the leaves, so you don't have that desiccation occurring from wind. And examples of C4 are the poaceae, the grasses, and other plants, and they're more drought tolerant, so we use those as a perimeter guard. Finally, the CAM plants, which their stomata are typically closed during the day to prevent desiccation, are used as our perimeter plants and wind breaks to break the wind. Once we model our site and determine what plants we use, we create a wind break with CAM plants, an interior break with C4 plants, and then C3 plants in the middle. Water strategy is important. I love to use HVAC condensate, recycle instead of adding potable water, and HVAC condensate has worked well for us. You can also collect an enormous amount of dew from the roof here in Florida. And the last point that I would leave you with is we believe wind is the killer of green roof. And without a parapet, you've got to look at right plant, right place. Once you have that perimeter planting set, then your roof can be a success with biodiversity at higher taxa. And that wraps up my portion of the talk, and I'll pass it along to Joe.
Hello there.
Okay, Joe.
There we are. I'm Joe Webb. I'm an architect in Houston. We do a lot of commercial projects, but we also had a couple of clients of late who wanted to investigate green roofs because they have buildings that they build to keep. So they're looking long-term investment, long-term utility operating. So one of the first things we started looking at, and this particular water map relates to a building that we have just finished about a year ago on the Gulf Freeway. And if you're familiar with Houston, the Gulf Freeway runs from here to Galveston. We are immediately adjacent to the freeway. We have city water. We have no city sewer access and can't get it to us within a quarter mile. So we had to go multiple different ways to make this thing work. So we approached the state agencies and we have an aerobic septic system that uses our 17,000 square foot green roof as its spray field. So we actually, on this particular building, can basically meet the requirements of the water pedal of the Living Building Challenge. But it's a pretty amazing situation, the fact that we thought we had a real problem and we figured our way out of it. Like Kevin, we capture a lot of condensate. We capture about 100,000 gallons a year on this particular building. We also, and just to give you some numbers on the green roof itself, 73% of every raindrop that hits it never leaves that roof. So we hold about 330,000 gallons over a year at that point. We also, because it is a green roof and it does have drainage, we also only put about 130,000 gallons into a cistern. The cistern you see there at the bottom, if I can get this pointer to work,
just click on the cistern, Joe.
Yeah.
If you just point and click right at the cistern, there you go.
I just learned something. That cistern, we have put about 2,500 lineal feet of 48-inch pipe under our parking lot, and we hold 395,000 gallons of water there. And if you've been familiar with Houston of late, we've gone basically 5 months without rain. In fact, we had about a ½ inch yesterday and about 1.5 inches this morning, and we're still 20-some-odd inches behind. And like Kevin was saying, we're used to 48 to 60-some-odd inches of rain around here. So this is, for us, very interesting situation. But of the 5 buildings that we have that have green roofs, not a single one has lost any water, in the fact that we still have water in our cisterns. We are still, and we irrigate our green roofs, not unlike Kevin. We actually irrigate because we can go longer than some without rain. But give you another little, this is even better. This will give you some of the numbers I've been throwing around. Our site, we have the first commercially approved gray water system in the city of Houston, because we also supplement from the cistern and from the condensate. The aerobic system, our site is a little tiny site. It's only 1.65 plus acres. It has 27,000 square foot of office building. It has parking for 90 cars, and yet we are 43% green on that site because of our green roof. And we hold 2.238 acre feet of water before we discharge. When we discharge into the state's system, which only can accept originally from an equivalent of the undeveloped site. So we had to make sure that we did not overflow that, and so we do. We treat that stormwater before it goes up. We filter and we settle things out. That's how our basically our aerobic system works. We actually irrigate the roof. Another reason for us doing green roofs, and this is back to the heat part of the equation, is we did some calculations and have now realized that we can decrease the air conditioning capacity or need for capacity on the building by a significant amount because of the evapotranspiration characteristics of the green roof. All of our green roofs are intensive. The shallowest is 9 inches. The deepest is about 12. We also use basically about a pallet of 4 native plants. Wind-wise, that one maybe is a little too small, so I'll skip to the next one. And this comes back to some of what Bill alludes to, because our first green roof building went through Hurricane Ike with average 110, 120 mile an hour winds sustained. And our friends at NASA, which are about 3 miles away, told us they had some recordings of 140 mile an hour gust. This green roof didn't lose any plants, didn't lose any of the walkway stone that we used. We used a lava rock as our pathways and as our perimeter so that you can get in and repair flashings. Didn't lose a bit of it. And I was up on the roof 7 days after, because that's the earliest I could get there, and photographed it. And you'll see it in a bit. There's just literally no change. And what we finally figured out, what we did is, and we had some of this purposed. This is not a publicly accessible roof. This was our experiment roof. We purposely kept our parapet down at about 18 to 20 inches. Most of the plant material we have tops out at about 18 to 20 inches. We do have Gulf Coast muley on this roof that is 4 feet tall at this point in time. But we realized what we did is we moved the boundary layer up because of the parapet and because of the plant growth, and took away the scouring motion that you would normally see on a green roof. So we did it by luck, and we did it by a little bit of planning that we didn't quite fully understand. So I'll take luck any day of the week at this point. But so just a bit of that to give you some ideas. Because of our green roofs, we have an R value of 66.235. That's on the 9-inch depth soils. One thing on heat, we have temperature probes 6 inches above, dead center of, and at the bottom of our green roofs. And I'm still compiling data, so you'll have to bear with me on some of this. We have data that goes back 3.5 years. And what we're seeing is the air temperature can be 95 degrees above that roof. Mid-roof, it will be 85, 88 degrees, and at the bottom, it can be 82 to 85. We have gotten as low as 78 in the summer. And I've got a client trying to maintain building interior temperatures at 72 to 74. All of a sudden, I've only got to make up 8 to 10 degrees temperature differential on my biggest heat sink, which is the roof. So it has made a significant difference. And the bit I was telling you about decrease because of that green roof. First building went in, engineers just flat didn't believe our numbers. They said they have to have a 250-ton system. Luckily, it's a multi-stage. So we've never activated more than 120 tons of the system because we track it. So the second building, which is a mirror twin, we actually decreased to a 140-ton type chiller and added my client calls it a clean manufacturing area. It's technically a clean room. It's a controlled environment. And did not stress that 140-ton system because all of a sudden the fact that we have all of this excess envelope capacity built into the building. The other thing we found out is our green roofs average about oxygen for 975 people a year. We only have a population of about 200 people in these buildings, so we're producing excess oxygen. We actually pick up airborne particulate. We're actually adding stuff to the roof, not much, 600 and some odd pounds a year. But we also estimate that we're saving like 42,000 tons of CO2 a year on these roofs. The roof itself, just to give you an idea of what it really kind of looks like in just a simple diagram, our plant material average of starts off about 8 inches deep. It's averaging about 20 now. Our soil's about 9. The soil is a very, very, we have a physicist actually help us design the soil because I want to be able to hold only a certain amount of water on this particular as to weight so that we can quite possibly use this on existing buildings. We'd have to thin it down, but there's possibility. So that gives you some basic ideas on that. And this was our roof 7 days after Hurricane Ike. Yeah, it looks a little windblown, but that's about it. So we actually did pretty well. We felt pretty good, and so we're very comfortable with what we're doing. Another image of that, the Gulf Coast muley here was very much bent over, but again, it's standing about 4 foot tall up there. And we actually have this all around our major air intakes in the building, and again, just to kind of adds a little extra filtration, a little extra oxygen off inputting. Just a real quick bit on the Living Building Challenge on our Gulf Freeway building. If we could have had our own water well or had a treatment system to create our own potable water, we would have had that one complete. And so finally, everybody's worried about habitat and the fact that, here we are building in a sensitive environment in an area. So does it work? Yeah. Now we have nests on the roof, and we have new goals. So with that, just a real quick hit on wind, water, and heat. And now to turn it over to David.
Excellent. Joe, I can tell you, I'm happy to see that picture from Ike. That would have been fantastic to go up there afterwards.
Oh, it was. It was.
So David, well, you're last here.
Well, hi. Does everybody see my presentation? Just want to make sure before we begin. My name is David Aponte. I'm an environmental engineer with a master's in water resources engineer. So I've been installing green roof for the past 8 years in Puerto Rico. So we've managed several installations along the ways and different alternatives that we come up with. And seeing everyone talk, come with the same with the question that should all green roofs be constructed equally? And I think the answer is quite simple. It's no. Every climate will have its own threshold, so we'll have different scenarios that you will need to address. We are basically located in the Caribbean. That's where Puerto Rico is. You can see it on the presentation. Basically, in the last 8 years, we have encountered that the industry has encountered basically economical disadvantage because due to our location, minimal social acceptance since we do have a lot of rain. Roofs tend to leak a lot here, so people tend to be afraid of green roof installation. And a lot of environmental constraints. So I'm going to stay in with the environmental constraint based on that we're talking about heat, wind, and the growing media. Here's a picture you can see. I call it the oven syndrome. You can see the bottom picture. You see how the roofs basically on red color, and this is on a cloudy day. You can see on the picture above. Typical roof construction here are based on just white color coatings on the roof. So here's a picture that we see. This is basically one of our first green roof. This is an experimental roof that we did. You can see how the green roof fits in the middle between two different type of roofing material. The first one is white color coated. The other one is a metallic asphalt torch roof. In the middle, it's the green roof. See the difference in colors and the difference in temperature. Prior to the green roof being installed, we measured their temperature, and we recorded average temperatures of 182 degrees Fahrenheit up on the roof and 108 within the ceiling of the house. This is one of our environmental constraints. You see, there's a lot of publications out there with regards to green roof behavior along the northern U.S. and Europe, but I think we have avoided, or we have not foreseen that subtropicals and tropical regions, we do have different scenarios that we have to deal with, like excessive rain. For example, this Hurricane George here brought to the island approximately 40 inches of rain, so in just one event. And this is a Category 4 hurricane that passed through the island, so we're talking a lot of wind. This roof particularly was the first roof built in Puerto Rico. Was done in the University of Puerto Rico, and it was built based on the FLL guidelines, and it did pass Hurricane George. As we can see, it's basically the roof was intact based on different pictures and inspections that we did. Although a lot of people do not consider the roof as an good roof because aesthetically does not look pleasing. It gave us a lot of information with regards of what not to do or how to adjust different scenarios to make it work. For example, here they used black lava rock would tend to overheat the roof. So what you have is like burned grasses and other points like that. So in this roof, I think plant selection was not yet perfected. So yeah, I'm just going to show you some pictures of different roofs that have passed different scenarios, different storms, hurricane, tropical storms, different wind scenarios. And they're still there intact without any issue. So here's this one was done in, we call it Montellera. You see that's a combination of solar panel and a green roof. Basically a 2,000 square green roof project. It was done several years ago. This is a residential project. When you see we have the ballast on the perimeter, which was I think a 2-inch white gravel. Picture does not appreciate that, but it's quite big white pebble stone that would use, so it won't fly away during high wind scenarios. Calculations was done, and it has passed a lot of wind scenarios and still look as beautiful as we see it on the picture. There's another project on the west side of the island. I wanted to bring different projects and different scenarios on different locations because we have 6 different microclimates in the island. We can have a microclimate near the rainforest and on the dry forest that rains 30 inches. On the wet forest it could rain 200 inches in a year. So we have different scenarios and we have to deal with this constantly on each installation and each design that we do. This is another project in Bayamon. This is a 12,000 green roof project. It's still there and it's still holding up and hold up the last tropical storm that hit us like a month ago, and it still looks beautifully. This is I brought this project in because it's a small project, but it was a fun and entertaining project because we installed several edible plants. We were talking the other day, had corn, spinach, lettuce, you name it, it was up on there on the roof. If you can see, it's in the bottom picture. It's within a part of the house that didn't have no ceiling or roof. So it was we created the green roof over the second floor of the house, even though it's a 3-story old house in old San Juan, as you can appreciate on the picture. Even though during the economical crisis that we're having, we still managed to install big roofs that have passed a lot of wind scenarios. You have there approximately 10,000 square roof with 26 Almacigo trees on the roof. Basically, the environmental mitigation of trees were done on that roof particularly. And my last project, which I'm working right now as we speak, it's the Bayaha Historic Building, old barrack building, which is a 24,000 square feet green roof, which has solar panel integration. On the other 24,000 square feet of the building is basically half and half. Over here you can see we've done water retention of different small roofs, and on top of the small roof that were basically capture and use that water to create. We're gonna create a kind of a wetland on the roof to irrigate and provide nutrients for the existing green roof installation. So I think we're coming into the conclusion of my presentation. Try to make it quite fast, and so if you have any questions or the panelists have any questions,
okay.
Here we are.
Thank you, David and Kevin and Joe. I think we've done an excellent job. I think we're right at the end of our time. I know I learned a lot. We're also working with biodiversity. We actually have some bee monitoring systems on our roof from a young student at York University. David, I don't envy you being right there where all those tropical storms and high winds are coming over to blow the green roofs off. How about each of us take a moment, I won't say any more, but just give me some impression about what you thought of everybody's work and how we might be able to do something together in the future. So Kevin, do you want to start?
Thank you, Bill. I really like David's point about food. I'm a big rooftop permaculture enthusiast.
Great.
We grow lots of food on roofs. I think a big portion of the new gross domestic product is going to be food, and every square foot that people have in the urban core, they should be thinking on the wall or on the roof, how do I grow food here?
Excellent. And Joe?
And I agree. One of our clients has actually got a little event center in one of the small buildings, and they supply their vegetables, their fresh vegetables for that center off the stuff that's grown on the roof. So I'd like to find out just a little bit more how much you guys have been doing in Florida and just see what else we could pull off.
Excellent. And David?
Well, I was quite interested on plants selection down in Florida, since we have in some places similar scenarios down in Puerto Rico. So I think it's for me it's the plant selection and how do you manage to have a non-irrigated roof